Good morning, guys. Today we're going to end 6.2. We're going to focus on three things: finding inverse matrices, what the determinant of a matrix is, and we're going to review what the identity matrix is. Again, we need to know what the identity matrix is before we work with anything today. So please remember that the identity matrix, it's also labeled with I, is pretty much a square matrix. So it's 2 by 2, 3 by 3, 4 by 4, in which the numbers are ones and zeros and they follow a particular order. In the first row, the first element is a 1, then it's all zeros. In the second row, the second element is a 1, and then it's all zeros. In the third row, the third element is a 1, and then it's all zeros. Besides the constant. If there are constants, with a dotted line, besides the constant, okay? Just the identity matrix on the left-hand side, ones and zeros. Now, why do I need to know what the identity matrix is? Because it's very helpful in order to find the inverse matrix. There are a couple of ways to work finding the inverse. If they give you two matrices and they ask you, are they inverse? It's a very simple process. All you have to do is multiply A times B and check to see if you get the identity matrix. And then you also have to multiply B times A. And if you get the identity matrix again, that means they are inverse. So let's try to do this process. And again, just in case, this is example 5, this is example 4, page 379. So first, again, remember, this is 2 by 2, this is 2 by 2. They are equal, so I can multiply them. My resulting matrix will be 2 by 2. So I'm going to get a resultant matrix, AB, that is 2 by 2. These are circles that represent my answers. Now remember, I'm going to choose the first row and the first column and multiply. -3 times 1 is -3. 2 times 2 is 4. I'm going to add these two, and my first element will be a 1. Now I'm going to use the first row and the second column. -3 times -2 is +6. 2 times -3 is -6. When I add them, I get a 0. Now I'm done with this row. I'm going to use the second row and also the first column. -2 times 1 is -2. 1 times 2 is 2. When I add these two, I get 0. Remember, those are just circles representing they're placeholders. I'm just rewriting it so you can see it. And now I'm going to use the second row and the second column. -2 times -2 is 4. 1 times -3 is -3. When I add them, I get 1. So again, I got the identity matrix. So AB is good. Now I also have to do BA. It's not good enough to just do AB. So AB is good. Let's try BA now. Again, as I told you guys, it's always better to just rewrite the matrix so you can easily work with them. Do not try to multiply to the left. You're going to go crazy. Don't do it that way. So again, -3 and 2. That's a 2. And here I get -2 and 1. 2 by 2, 2 by 2. They can be multiplied. I'm going to use the first row and the first column. 1 times -3 is -3. -2 times -2 is 4. When I add them, I get 1. Now I'm going to use the first row and the second column. 1 times 2 is 2. -2 times 1, -2. When I add them, I get 0. Second row, first column. 2 times -3 is -6. -3 times -2 is +6. Add them, I get 0. Second row, second column, 2 times 2 is 4. -3 times 1 is -3. Add them, I get 1. That identity matrix. So I just verified that A and B are inverse matrices. Again, when they give you two matrices and they ask you, find are they inverse matrices? Just multiply them and confirm that you get the identity matrix. And I repeat, it is not good enough to just do one and get the identity matrix and say, oh, perfect. Because sometimes, remember, there's a directional element. A times B is not the same thing as B times A in the matrix. You can get an identity matrix in one and not in the other. So make sure you multiply them both, okay? So that's it for checking whether two matrices are inverse. Now, we're going to try to find the inverse if they give you a single matrix. So say they give me this matrix, 8, -3, -5, and 2. They tell me this is A. I want you to find the inverse of A. So again, it's, I want to find the matrix that when I multiply by this one gives me the identity matrix. How do I do this? It is another simple process which you know. All you have to do is equal this to the identity matrix. And you're going to write the matrix in augmented form. That means you're going to have a very big matrix. And what you want to do is you want to have the identity matrix on the left-hand side. So if you see these steps in the book, let's try to work on them. I'm going to multiply this one by 3, and I'm going to multiply this one by 8, and then I'm going to add them both. And let's see what happens. When I multiply this by 8, I get 24, or this by 3, I get 24, this by 3, I get -15, I get 3 and 0. Again, I multiplied the first one by 3. Why? Because if you can't cancel out these numbers just by adding them normally, so I have to multiply this one by this number and this one by this number. So I end up with two equal numbers at the end with opposite signs. You'll see what happens now. When I multiply the 8 times -3, I get -24. I get 16, I get 0, and I get 8. That is the first row multiplied by 3. That is the second row multiplied by 8. Now I'm going to add them. That's a row operation. This plus this. The resulting operation will give me 0, 1, 3, and 8. That is the bottom one because I added the top one to this one. That's the bottom one. Notice I already canceled out my first one. And on the top, I'm going to have this expression currently. This is a 24 minus 15 divided 3, 0. Now again, I want this number to be let's see what they did here. Okay, yeah. Now what they want me to do is I want to cancel out. I'm going to divide everything by 3, first of all, to simplify. I'm going to divide the top one by 3. So again, I'm sorry, this process is somewhat confusing. I'm going to divide the top number by 3 so I can simplify. So I'm going to have 8 minus 5, 1, 0. And in the bottom, I'm going to have 0, 1, 3, and 8. Now remember, in order to end up with an identity matrix on this side, I need 1, 1, 0, 0. In order to get a 0 here, I'm going to multiply this one by 5 and then add it. So when I multiply this by 5, I get 0, 5, 15, and 40. And when I add it here, I'm going to end up with, again, this is very confusing. When I add them, 0 plus 8 is 8. 5 plus minus 5 is 0. 15 plus 1 is 16. 0 plus 40 is 40. Again, this is Jordan-Gauss elimination. We did that about 3 days ago. And what do I do now? Again, I want a 1 here. I'm going to divide everything by 8. Again, this one was a little bit complex. And usually you're only going to get 2 by 2 matrices, not 3 by 3. Not usually. I'm not going to give you a 3 by 3 matrix, just 2 by 2. Divide the top one by 8. 8 divided by 8 is 1. 0 divided by 8 is 0. 16 divided by 8 is 2. 40 divided by 8 is 5. Now that I have the identity matrix on the left-hand side, the inverse matrix of the original matrix is this matrix. 2, 5, 3, 8. If you multiply that matrix by the original one, you will get the identity matrix. So again, to repeat, you equal your original matrix to the identity matrix, and then use Jordan-Gauss elimination or Jordan-Gauss elimination to end up with the identity matrix on the left-hand side, and the right-hand side will be your answer. That's pretty much it. Now note, you could end up with a situation that instead of looking like a very nice identity matrix on the left-hand side, again, very nice identity matrix, there might be some situations that after you try to eliminate via Gaussian elimination, you end up with something that looks like this, 0, 0, 3, 8. Remember, that means there is no solution to that system. If you end up with an inequality, 0 equals something, no solution. So you just leave it there, no inverse matrix can be found. That's it for this particular example. Now, again, you remember how complex. Let's write the original equation and you'll see how we can simplify things. And you'll see how the determinant is useful. Now you saw that very, 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 very long process, all it did was give me the following matrix. 2, 8, 2, 5, 3, 8. 2, 5, 3, 8. Again, that very, very long process, all it did was give me this. This is A and this is B. Now you'll see that there is a new way we can work with matrices that will help us find the inverse in a much, much faster fashion using what's called the determinant and scalar multiplication. Very simple process. First of all, what is the determinant of a matrix? Remember the determinant, we saw determinants when we're talking about, or it's like a discriminant, more or less. It's like just a value that tells you something about a matrix. In case of the determinant, all it does is tell you this has an inverse or this does not have an inverse almost immediately. Also, we're going to be working today with 2 by 2 matrices. Tomorrow, we're just going to do 3 by 3 matrices, but today is 2 by 2 matrix. Now, the determinant is quite simple. Let me turn this into letters so you can clearly see this. Let's assume these numbers are substituted by these letters. The determinant is this times this, A times D, minus this times this. That's it for the determinant. That's simple. 2 times 8, 16, minus 3 times 5, 15. In this, the determinant of this matrix is 1. That's it. Now, why is this useful? You'll see right now. But the first thing that this tells you is that if your determinant is a non-zero number, the matrix has an inverse. If you do the determinant and the determinant gives you 0, you can immediately say, there is no inverse, without even having to multiply. You don't have to multiply by the identity matrix or equal it or anything. You just say determinant equals 0. No inverse. Now, what do I do with the determinant? And even though this might sound tricky, it is actually a very straightforward mechanical process that will give you the inverse of the matrix immediately. Now, the formula to find the inverse of a 2 by 2 matrix, if it has an inverse, it's very simple. You take your original matrix, again, let's use letters now so you can see them. What you do is, in the 2 by 2 matrix, you always switch these 2 letters. So you're going to end up with D and A. and B and C stay exactly where they are, you just change their signs. That's step one to find the inverse. Again, flip these two numbers, sign does not change. These numbers stay where they are, the signs do change. And then you multiply by the inverse of your determinant. AD minus BC. And you'll see how simple I can find the inverse of this matrix instead of doing all that addition and Gaussian-Jordan elimination. Now, first of all, the determinant of this matrix we saw was 1. So I'm going to change this number for 1. 1 over 1 is 1. So you're going to do scalar multiplication with these values. Again, you're going to distribute the 1, multiply times everything inside. 1 times any number is, it's the exact same number, so nothing changes. So the inverse is pretty much D negative B negative C A. And if you notice, these two matrices, what happened with these two values? They switched position. And what happened with these two values? They changed signs. So again, instead of doing the whole Gaussian-Jordan elimination, I found my determinant, it's 1, very simple. Then I changed these positions, changed these signs, and multiplied by the inverse of the determinant. Now, sometimes this number will not be 1. It might be negative 1. Again, you distribute negative 1. And usually you're going to end up with small numbers, maybe 2 or 3. And these numbers will usually be whole numbers, but you might end up with fractional numbers. But that's fine. Again, if you multiply 1/2 times 8, you'll end up with 4. So these numbers are usually very simple and you get nice fractions, not, 3 over 17. No, you're probably going to end up with very nice fractions. So don't worry about it. And that's it for today's class. Let me go over the homework so you know exactly what you have to do. First of all, on page 383, I want you guys to do from 19 through 22. In these exercises, you're given two matrices and you have to multiply them and tell me whether you get an inverse or not. Again, that is if you multiply them in both directions and end up with the identity matrix. That's 19 through 22. I also want you to do 27 through 30. In these cases, you're going to set your matrix equal to the identity matrix. And then you're going to use Jordan-Gauss elimination to end up with your identity matrix on this side, and the resultant matrix will be here, the inverse. You're going to end up with the inverse here. That's 27 through 30. And finally, you're going to do 35 and 36 using the last method we just did. You're going to, let me see. Okay, it's fine. Yeah, they have inverse. They have inverse. Okay, perfect. You're going to do 35 and 36, finding the determinant, and then just switching the signs, switching the positions, switching the signs, multiplying by the inverse of the determinant to get your inverse matrix if it is a non-zero determinant. That's pretty much it for today's class. If you have any questions, let me know. Remember, Friday, it's going to be a just totally practice day, exercises. And if you have questions, we can set up a Skype call. Tomorrow, we're going to work on 3x3 matrices. So make sure you get this down and you're very clear on how to work, because you need to understand this very well in order to work tomorrow. Tomorrow is a slightly more complex process. Have a great day. Any questions, let me know.